In this lecture, you will study about angular velocity, angular acceleration, and their relation with linear velocity and linear acceleration, torque, and angular momentum. Angular velocity and its relation with linear velocity. The figure shows rotation about a fixed axis. A particle P of the rigid body rotating about the fixed z-axis moves in a circle with center C on the axis. We know that the linear velocity vector v of the particle at P is along the tangent at point P to the circle. The angle PCP dash describes the angular displacement delta theta in time delta t. The average angular velocity of the particle over the interval delta t will be omega, and that is equals to delta theta by delta t. And to find out the instantaneous, delta t will tends to 0, and that will be equals to limit delta t tends to 0 delta theta by delta t. And the linear velocity is limit delta t tends to 0 delta s by delta t, as we have studied in the kinematics also. But delta s is equals to delta theta into r. Theta is equals to arc upon radius. So you can say that v is equals to omega cross r. And omega, r and v are mutually perpendicular to each other, because v is the cross product of omega and r, and you can find out the direction by using right hand thumb rule or screw rule. You know the equations of motion. V is equals to u plus at, s is equals to ut plus half at square, and v square minus u square is equals to 2as. So in terms of rotational motion, instead of v, you will use omega, u omega naught, a alpha. So you will get omega is equals to omega naught plus alpha t. Theta is equals to omega naught t plus half at square, and omega square is equals to omega naught square plus 2 alpha theta. And this we have already done in kinematics also in case of circular motion. Example based upon this concept, NCERT 7.14. Here the angular speed of a motor wheel is increased from 1200 RPM to means revolution per minute to 3120 revolutions per minute in 16 seconds. You have to find out what is its angular acceleration. Angular acceleration and how many, assuming the acceleration to be uniform, and how many revolutions does the engine make during this time. So omega naught will be equals to 2 pi into angular speed. By using the equation omega is equals to omega naught plus alpha t, and by putting the value you will get the value of omega naught. Similarly, you can find out omega, and you know that angular acceleration is omega minus omega naught, means change in angular velocity upon time taken. So you will get 4 pi radian per second square, and the angular displacement will be calculated by using second equation of motion, that is theta is equals to omega naught t plus half alpha t square, and by putting all the values you can find out, and that will be 1152 pi radians, and number of revolutions will be angular displacement upon 2 pi, and that will be 576. torque or moment of force. As in linear motion, we have studied about force. In rotation motion, to move any object in rotation, we require a force, and that is the torque. So you can see that the rotational analog of force is moment of force, and that is also called as torque. If a force acts on a single particle at point P as shown in the diagram, whose position with respect to origin O is given by position vector R, then the moment of force acting on the particle with respect to origin O is the vector product of R and F1. The moment of force therefore will be a vector quantity, and the magnitude will be Rf sine theta, and direction you can find out by using right hand screw rule. The vector force F can be resolved. F sine theta can be used as torque. So mathematically, torque denoted by the symbol tau is equals to R sine theta into F, or you can say R perpendicular component into force, as shown in the diagram in previous slide. If the direction of force is reversed, the direction of moment force will also be reversed. Angular momentum or moment of momentum. Rotational analog of momentum is moment of momentum or angular momentum. Consider a point P whose position vector with respect to origin O is given by position vector R, experiences linear momentum P, then the angular momentum of the particle with respect to origin O is defined as the vector product of vector R cross P vector. So it will be a vector quantity, and the magnitude of this angular momentum denoted by symbol capital L will be equals to Rp sine theta, and its direction is given by right-handed screw rule and is perpendicular to the plane containing R and P. And in this case, it emerges out of plane as shown. Similarly, again R sine theta is a perpendicular component, so L will be equals to R perpendicular into the linear momentum. And again, if the direction of P is reversed, then the direction of angular momentum will be reversed.